So in this lecture, we are going to study the capability curve of synchronous generator. You can see the equivalent circuit of synchronous generator here, where E is the induced EMF, V is the terminal voltage when the machine is connected to infinite bus. This is the electrical point of infinite bus, the voltage corresponding to the electrical point of infinite bus, and X is the total transfer reactance from E to V. Now, initially, if we don't discard the resistance, then it will be V plus Iz. E equals V plus Iz, as you may know, where Z, the impedance, is equal to R plus Jx. And for the purpose of simplified equivalent circuit, we discard R. So impedance we assume as Jx only. So the induced EMF equals V plus Ix. Now let's go to the phasor diagram. You have this voltage, the terminal voltage as V and the current as I. Now, according to the power factor, or according to the lagging or leading current that is drawn from the generator, the angle between terminal voltage V and current I is given as phi. And you have this drop Ix, which is perpendicular to I, and V plus Ix gives you E. So this is what represents this equation, E equals V plus Ix. Now the angle between E and V decides the active power delivered, which is power angle del. Let's see the vertical axis here and the horizontal axis as this. And we mark these points as A, B, and C. And if we multiply the sides of this triangle AB, BC, and AC with V by X, that is terminal voltage by transfer reactance, V by X, then what will you get? What is AB into V by X? Which is already AB is V, so V into V by X will give you V squared by X. Now, what is BC into V by X? Ix is here. Ix into V by X is Vi, and AC into V by X will give you EV by X. So let's change the phasor diagram now in terms of this V squared by X, Vi, and EV by X. What is the peculiarity of these terms? Can anybody say? What is V squared by X? What is Vi, and what is EV by X?
Power.
Yeah, power. So V squared by X is related to reactive power, and Vi is related to apparent power. Then EV by X is related to active power. So we change the triangle now to this one, and again the horizontal and vertical axis are drawn, and the horizontal axis represents the reactive power and the vertical axis represents the active power. Now, reactive power will have both sides because the generator or a synchronous machine which is operating in generating mode can either draw reactive power or deliver reactive power. So we have this positive side and negative side of Q active for the capability curve. Now, what about the active power? For active power, we don't have the negative side of the vertical axis because we assume that the machine is in generating mode. We are going to draw the capability curve of generating mode, not the motoring mode. So basically, this is the region. The first and second quadrant will come into picture here. If P is the vertical axis and Q is the horizontal axis, the whole region, in these regions only we have the capability curve of the generator. We'll see the locus later, but this is the region. Okay, anyway, in these regions it's not active. Okay, now so the quadrants are decided now. Now we are going to draw the capability curve itself. Say we take Vi as the radius and draw a semicircle. What is Vi here? This is Vi, right? If we draw a semicircle like this, okay, now this is what we are trying to do because Vi is the complex power. Complex power can be decomposed into active and reactive power. So when this vector moves along a, with the tip touching a locus, then the active power is changed and the reactive power is changed accordingly. So the total range of active and reactive power dealt by the synchronous machine, or the maximum active and reactive power that can be delivered by the synchronous machine, that is decided by this locus, the maximum, the tip, the how much the this radius can elongate. Okay, so we'll see that. Now let's see this first. What about the phasor E? This one, this is phasor E, right? Phasor E, when the load increases. When the load increases, we have increased current. Increased current in the sense, we have already assumed that the circuit, the power system circuits are more of reactive in nature. So phi will also increase. If phi increases, the inclination of the I will move to this side. How I will move down. Okay. When I moves down, what about E? What will happen to E? Anybody? When I moves down, or when phi increases, what happens to E? E will increase, right? More E is required now, or more induced EMF is required now to compensate for the reactive power, for the increased load current. Increased load current in the sense, basically I squared X is increasing in the circuit. So this I squared X must be delivered by the machine. Accordingly, the field current excitation should be increased. But what is the field current limit, or what is the extent of field excitation increase that can happen from the rotor side? We have a field limit with respect to rotor field winding heat limit, right? So up to that point only we can increase the field excitation. So this locus, basically here, this locus will give you the overexcitation limit. If this is Emax, for the induced EMF, if the maximum limit is Emax, this corresponds to the increased field current, and whenever the field current hits the maximum limit, this locus gives you the overexcitation limit. So this part is a section of capability curve. Now beyond this part, we have to decide how to draw it. Okay, so this is a part of locus of this capability curve. Okay, now what happens if the field current is very low? Here we have seen that the field current hits the limit, so E is Emax. Similarly, we have a lower limit for field excitation as well. That is, for the minimum field current, the generator absorbs reactive power. For Emax, the generator delivers reactive power. That is why this is at the positive Q, positive Q axis side. And for the minimum field current, or the under excitation limit, it is in the negative Q region. So let this be the, here there is a cut, you can see, let this be the under excitation limit. So this is the over excitation limit and this is the under excitation limit. So these two parts are, these two sections are two sections of the capability curve. Now we have to find the remaining parts of the capability curve based on active power limits. So this is completely related to reactive power limits, this over excitation limit and under excitation limit. Now what decides the active power limit? We have the stability limit with respect to power angle del. So here we have the angle between E and V as del, right? Now ideally or theoretically del can go up to 90 degree. So this should be the Pmax, the vertical line here, this should be the Pmax. But practically the machine does not operate here. It should have enough stability margin, sufficient stability margin. So it will operate somewhere here only. So that is why this curve is given here. This curve corresponds to the Pmax of the machine with respect to stability limit, or with respect to the range of power angle. Okay, now when the system load is increased, there is a steady state increase in the, if there is a steady state increase in the system load, then the generator delivers more active power, which means the stator current is more, right? Stator current is more. So the whole locus of the active power limit should correspond to the stator overcurrent limit, because stator heating should not happen. It should not be overheated. So this locus corresponds to the stator overcurrent limit. So this is the stability limit, P limit with respect to stability. This is P limit with respect to stator overcurrent. This is E limit or field current limit corresponds to the Q limit, maximum Q limit. This is the minimum Q limit. So based on this violet curve which is shown here and the area inside, this is what is a capability curve for the machine. Now here it is written that the negative side of Q axis or the negative horizontal axis corresponds to mostly night operation, and the positive side of the Q axis corresponds to mostly daytime operation. This may not be always true, but based on the normal load curve of the standard load curve of the power system, we know that industrial loads are there, and Q, X may dominate C at daytime, and C may dominate L during night time. So in that case, the reactive power will be delivered by the machine. It should deliver reactive power at the daytime, and it will absorb reactive power in the night time. This again depends on the induction machine loads and other things, but as per the standard load curves, this suggests daytime operation and nighttime operation with respect to positive Q and negative Q. So this is what is the capability curve of synchronous generator.